Welcome to all of you for joining us today. I'm here with Pierre Govarts, who is BioMedware Chief Scientist, and I'm Jeffrey Jacquet. And today we'll be talking about joinpoint regression analysis, hypothesis formulation, and testing in Vesta. So first, acknowledgements. NIH has played a significant role in getting Vesta in place. So a lot of R&D went into this, developing this tool. In particular, we had funding from the National Cancer Institute, the Library of Medicine, and Environmental Health Sciences, NIEHS. We also had funding for the commercialization activities from the Ann Arbor Spark Business Accelerator, and also from the Michigan Economic Development Corporation. Thank you to all of them. Pierre and I have been knocking around a long time, obviously me longer than Pierre, who still is a striking figure. And Pierre especially has built an enormous reputation for himself internationally in the field of geospatial analysis with a focus on geostatistics. And you'll be seeing some of the product of his innovative research and work today. So what are we doing today? We're going to give you a quick overview of the Vesta platform. We'll then go on to joinpoint regression, trying to understand how one can look at trends through space and time. Pierre will then talk about handling compositional data itself and some of the challenges, which is a great contribution of this webinar and our research to geospatial analysis. And then Pierre will undertake a live platform demonstration running Vesta Live. And then we'll have Q&A. Now, if you would, please, as questions arise, you should be able to use the Q&A tab on your screen to type in those questions. So as they come to mind, just type them in. We'll be filtering them a little bit. I won't, but the wonderful people in the background will. And then Pierre and I will endeavor to answer them. Now, also at the very end, after this is over, you will receive an email within a few days with a link to the webinar and also a link to the data set. So you'll be able to do exactly what Pierre does, provided you download a free trial of our Vesta software from biomedware.com. Okay, short overview. So when I think about Vesta and how we formulated it, it really supports 5 steps that I think are really essential in trying to understand and learn from space-time data. The first is rapid visualization using linked windows and statistical and cartographic brushing. You'll learn more about that today. To try to understand patterns, display patterns, understand them, and generate hypotheses. So that second step is hypothesis generation. And if you've come with a prior hypothesis, it's to begin to explore that prior hypothesis. After that, one moves on to modeling and using some of these statistical techniques, in particular geostatistical models today, to understand what's going on in the data, to try to understand processes underlying those patterns you've identified. And then we get to hypothesis testing using the models and also inferential statistics. Now that together then moves you on to knowledge discovery, moving the ball forward so we have a better understanding of our world and of your data. That's the Vesta mindset. So who can use it? Well, we're really focusing on geospatial analysts, and this can be drawn quite broadly. Our initial focus is epidemiologists, environmental scientists, social researchers, and policy analysts. But we also have economists using it. We have applications in ecology as well. What makes us unique is this ability to take advanced statistical methods, make them accessible through intuitive workflows. So what we're looking for is for this software to be accessible to novice users as well as specialists. All of this is available just for one subscription fee There are no additional charges. So it's a subscription model and very cost attractive. You can check out costing on our website. Okay, Vesta features. To do all this with visualization, of course, we must import the data, and then you visualize it and try to understand it. We handle missing data, both in visualizations and in analyses, which is a unique contribution in the world of GIS. Of course, you can work with multiple map layers from different data sets, control the display order, so you can do map overlays and just look at relationships between different layers in the data. You'll be doing some of that today. And again, as I said, rapid analysis. So statistical, cartographic brushing, linked windows, and then moving on to space-time geostatistics. Big contribution you'll be seeing today that Pierre has put in place is taking pre-existing only time-based joint point analysis, a spatial joint point, and extending it to space-time. And this, as you will see today, yields unique insights that otherwise are not available. So we also have, you won't see this today, more geostatistical methods and techniques for space-time multivariate data. And we also have extensions to machine learning and other things that Pierre will talk about. So there's a lot in here. Here are some example use cases you'll be seeing today: detecting shifts in cancer trends in epidemiology, environmental health, looking at pollution and exposure. You can also look at those in relation to health outcomes. Policy evaluation, a big topic today. What is the impact of an intervention in a population that's distributed through space and time? We also have use cases in ecology and urban health. So onward then to the good Dr. Gobart, who will take us through.
Thank you, Jeff. Yeah, I'm going to introduce for the concept of geographical joint point regressions. And I think some of you might be familiar with joint point regressions. And then to illustrate the concept, the methods, I'm going to use this data set. So what you see here is the county-level percentage of people diagnosed late with prostate cancer across the state of Florida. You have white male, black males. And what you can see when you look at this 3D visualization of space and time, you can clearly see this overall trend across time of getting more and more blue in the map, so which means a decline in the percentage of late-stage diagnosis. We can see strong disparities between the two ethnic groups, more red for black males, and also we can see this geographical disparities across the state of Florida. Now, in most situations, what people will do is only look at the plot on the right. So they will just look at two curves across the state of Florida, again, this average, and they will see, okay, yeah, there is indeed racial disparities, higher rate of late-stage diagnosis for black males, and we have a decline that started around 1990s, but that's it. And so we are missing a lot of the information about space. Now, to model this curve, more and more there's this technique called joint point regressions. And I think thanks to a freeware developed by the National Cancer Institute, more and more people are using this method, even outside the field of epidemiology. And actually, joint point regression model is just a series of linear or log linear segments, in this case, that are being used to model this trend. And so there is a connection between this linear segment at specific time, and we call this a joint point. So if you look at this curve, there are two joint points, one in 1989, one in 2000. So joint point represent, in this case, years, but in general, it's the timing for statistically significant change in rate trend. And so what we can see from this graph is that at the beginning, we have this slow decline in the percentage of late-stage diagnosis, and then it accelerates after 1989 until around 2000, and then 2000 it starts increasing. And the rate of change can be captured using a statistic called the APC. So it's the annual percent change is based on the slope of the segment. So it's just telling you in the first part of the curve, on average, there's a decline of 0.5% per year. Then it accelerates to close to 10% per year. And then it actually increased after 2000. And to just summarize all this information, we can also use the APC, which is the average APC over the entire time period. In this case, it's minus 3.9, so 3.9% on average over the 30 years. So why are we interested in this model is because, as Jeff mentioned, this can be used, in particular, if you look back at the past, to look at the impact of policies or intervention. In this case, for prostate cancer, there was the introduction of the PSA test in the late 90s. And then it's also used for planning. There is always goal, 2030. I mean, where are we going to be in terms of cancer late-stage diagnosis, 5-10 years down the road? So what you can do is extrapolate this trend. Now, this curve that I showed you was for the entire state of Florida. What if we start looking at different counties specifically? So here I'm just showing you 5 time series for 5 different counties across the state. And for example, if you look within the dashed circle, we are here in the Florida Panhandle. So there's sparsely populated populations, lower access to screening. And so on average, and it's what the color scheme showed you, on average, the percentage of late-stage diagnosis will be greater than in other parts of Florida. And if you look at the trend, it's very interesting that in the first part of the time period, you see the increase in the percentage of late-stage diagnosis. If you look a little bit more to the west, we have another county, and actually it decreased right from the beginning. You see these strong geographical disparities just within a few hundred miles. And then you see all the trend for the 3 other counties. So you see all the time trends are very different. And so it just shows you that analyzing temporal trends outside the spatial framework is unsatisfactory because you can have huge variability even across a single state. And it's very interesting to look at different counties and try to understand why in that particular county it started declining right from the beginning, and there it started increasing, and try to understand what happened. And as Jeff mentioned, so we have the freeware from NCI, but Vesta is really the only software where you merge both the joinpoint regression and the GIS. So you can explore the characteristic of all these time series geographically. You can also map some of the statistics I introduced. So you can, for example, map the APC. That's going to tell you that, again, in some part of the Florida Panhandle, basically the rate barely changed during the time period. In other part of the state, we have a decline that can be up to 6-7% per year. And what is also very interesting is the timing for this particular decline. So here I'm mapping the onset year of the decline. So basically the joinpoint for the first significant decline. And you can see in some part of Florida, it started very early, like in the early 80s. In other part of Florida, you really have to wait until the mid to the late 90s to see a decline. So again, there's a lot of interesting information that can be visualized and analyzed across space. Now I want to go a little bit further and talk about compositional data analysis. And you may never heard of the term compositional, but I know that most of you actually are manipulating this type of data. So basically, compositional data is just, if you look at I wouldn't say the mathematical definition, but it's just a collection of non-negative measurements that sum up to a constant values. Think about percentage of people diagnosed late or early or different stage, like 4 stages. You have 4 different categories where you have 4 different percentages that are going to sum up to 100%. Right. And so we experience this type of data a lot because a lot of our studies in the field of epidemiology are based on counts. Could be, number of infant deaths per county, could be even number of hours for different physical activities. And so this information is expressed as percentages or proportions. And the focus is typically on the relative frequency, not the absolute frequency. So we want to, compare the different groups. And so here there are two examples. The first one is actually the one I'm going to use to illustrate Vesta. Is the causes of mortality expressed as percentage of death from, and here I have grouped all the type of death in 7 different categories. So infectious disease, cancer, cardiovascular diseases, and so on. So we have 7 categories. And again, in each case, the sum of the 7 percentages should be 100%. Another application outside the field of epidemiology, I worked a lot on the Flint drinking water crisis. In this case, we were interested in the composition of the water service lines. And again, for a particular zip code, for example, would be interested in the percentage of lane that contain lead, copper, plastic, or galvanized material. And again, you have 4 different options, 4 different categories, and the sum will be 100%. Now, I want to illustrate the challenges. So why is it challenging to analyze this data? Because they're not free to vary independently, because there is a constraint that this should sum up to 1 or to 100%. So here's an example for the cause of death. They have this constraint both across time and space. So for example, if we look just for 3 of the main cause of death, cardiovascular diseases, cancer, others, as the percentage of mortality caused by cardiovascular diseases, so the green curve, decrease over time. Because of these constraints, it means that the contribution of the other causes, like cancer or other causes of death, has to increase. And it's the same if you look across space. You will see there's actually more death caused by cardiovascular diseases in the Upper Peninsula. And conversely, you will have lower cause of death by cancer or others, and again, because of these constant constraints. And because of that, you cannot analyze this data of these different variables independently. So you need to consider this data as a whole set in any spatial and temporal analysis. And so what we have implemented here, and again, it's going to happen behind the scene, is a joinpoint regression of compositional variables. We're going to transform the variables, create what we call log ratio. We are combinations of these variables. We're going to model, apply joinpoint regressions to these log ratios, and then we're going to back transform the time trend models. And so what you will see in Vesta is the end product. But what is interesting is because we're doing that, we guarantee that for any given year, the predicted percentages of mortality will sum up to 100%. So we're really consistent. Oh, no, I shouldn't do that.
Okay.
Yeah, no, it's a time to tab.
Yep.
Right,
there you go.
It's the time to illustrate Vesta, and I'm very excited to show our Vesta product. So when you start Vesta, this is what is going to appear. So you have different options. You can create a new project. You can open the project that's going to happen here because we already have created the projects. And you have some help menu. We have some demo video just to illustrate the use of Vesta. What's news if you want to know, what are the latest development in Vesta, or what would be interesting for you is we have a series of sample projects. So if you start Vesta, you don't have any data, or you don't know how to format the data, but you want to use it, we already have projects that were developed for you for the Flint drinking water crisis. Some are purely spatial, some are spatial temporal. You see, this is one of the projects we'll be using today, Michigan cause of death. So you can just download the project or load it and then start using Vesta. So in this case, I'm going to open the project that I created. And here it is. So when you start Vesta, you will have 3 main windows. I mean, here we have the data view, and you will see I have all the different variables I mentioned for the causes of death, infectious, cancer, and so on. And I'm looking at the entire Lower Peninsula, and then I will use a subset at some point. So I have two different geographies, but these are the data I'm going to use. So this is the data panel. Here you have the main panel. This is where all the results will appear, and these are organized at workspaces. And so basically you will see in each workspace, you can display up to 4 different visualization, and you can create as many workspaces you need. You will see we have here a time slider at the bottom. And when we display maps, we can just use a time slider and see how it changes over time. Here we have, some people don't see it, but there's a methods here panel. So there's a different method available. Jeff mentioned most of them. We're going to use mainly joinpoint regression here, but you have machine learning. We have a lot of geostatistical interpolation. We have different type of kriging, kriging of categorical variables, mapping of uncertainty. We have some multidimensional scaling as well, and the local clusters analysis, more and Xi. And then the other panel here, this is where you could actually import. You can actually here open a project as well if you didn't open the project at the beginning. You can also save your project, very important. For the data, this is where you can import more data into the software. You can do basic calculation. If you have different, let's say, zip codes, you can calculate the centroids. You could do a log transform of your variables. What we are going to use mainly is the visualization tab. So we have a lot of visualization tools available. You can create map, you can look at the data in the table. We have different charts, histogram, cumulative distribution plot, box plot. So these are univariate. If you have more than one variables, you may be interested in scatter plot, heat map to look at correlation between two. You even have a 3D scatter plot if you have at least 3 variables. The results, you can actually show some of the results plot and maps. In some cases, for the classification of categorical variables, we have contingency tables, ROC curves. We're not going to use that today. What we're going to use is the visualization related to temporal trends, because we're going to manipulate time series. And I'm going to use the first 2 values by geography distributions, and then you can also display the results. And then we have the report that you will see that every time you run a method, you are going to create a report with the results. We'll show an example with joinpoint regressions. You can visualize the report in Vesta, or you can export it as a PDF file. So let's start. And actually, when you visualize, you can either use this panel, or you can just left-click on some of the data. So let's look at cancer, and I would like to create a map of cancer. I can visualize, create a map of cancer rate, put it in workspace 1. And let's look at workspace 1. So this is a map of, percentage of death caused by cancer for a given year. So typical GIS maps, there are different things you can do here in terms of customization of the maps. I like the fact that you can change the background. I like to use satellites, but so I can use satellite background. Of course, you can zoom in, zoom out. You can do queries if you want to know, what's happening, what's the name of these counties, and what are the values. So that's something you can do easily. And if you don't like this color scheme, you can always go and change the color scheme here. There are different settings. Personally, if you want to increase the number of classes, I like to use the diverging color scheme if you want to go from blue to red, for example. And as I mentioned, there is a time slider here because this is a time series. So these actually are the value for the beginning of the time series. And what you can do is you can slide it and see what's happening in different times. And you can see that as we progress over time, there's more and more red in the maps because the color scheme is not going to change. So you can see in the illustration that we have an increase in the rate of, in the percentage of death caused by cancer as you move across time. Now, you would like maybe, and I'm going to access the visualization using Vesta. You may want, for example, to look at the histograms at the same time, just to have a value for this cause of death caused by cancer. And again, you have the same. So you will see that as we move over time, you will see that you can look at the statistics, and I'm going to just remove or lower it, so we have more space to look at the histogram, and you can see how it fluctuates across time. Now, since it's a time series, another way to visualize it is actually to look at the different time series, because right now what we are doing is just looking at the distribution in space and using the time sliders, but we can actually look at the actual time series, and I can use the option value by geography. So what did it mean? It means that I'm going to display the time series for each of the geographical objects. These are here the counties. And so now we start, having the spatial and temporal dimensions, and all these different graphs are linked. And so we can select some of the counties in the map, and we can see where the values fit into the histogram for a given year. We can actually start, again, moving the time slider is going to change. But you also look at the time series and see, which one is which. So you may want to see, okay, which one has this very high values, and you see actually it's the counties where the cause of death by cancer is pretty high. And so it's interesting. Quickly, you can really identify it in the maps. And sometimes when you have many time series, like here you have 68, might be difficult to visualize the trend. So what you can do in this case, there is another plot you can do, which is distributions. And what you can do in that way is just for each year, for each time period, is going to create a box plot. So you can see indeed there is this increase in percentage of death caused by cancer across time. Okay. Now, this is just one variable. Besides the cancer, we may be, for example, interested in visualizing cardiovascular disease. So I'm going to create a map of cardiovascular diseases. And I'm going to use the same workspace. I'm just going to replace the histogram here by that maps. And again, you can see the value here. I can quickly customize it. Go from, again, diverging, go from blue to red. And what is interesting in this case is the correlation between the two maps and how it changed over time. And so I can create the same things. I can create the time trend, let's say, for cardiovascular diseases. And let's put it here. And here you can see clearly, that as we mentioned in the PowerPoint presentation, we have this increase in the cause of death by cancer, but then there's a decrease in death caused by cardiovascular diseases. And so we have this global trend. And again, you can select one time series and look at which county it is. So we could look again at this one here. They had this high values for cancer and not so much for cardiovascular disease. But again, it's because they are correlated. And you can do the same here. You have this increase, this peak in percentage of death caused by cardiovascular disease, a basic decrease here. And it's interesting that these two counties are just next to each other. So you see how just going from one county to the next can create strong disparities. Now, what we have done here is just an exploratory data analysis. What we want to do is to move to the modeling stage using joinpoint regressions. And in this case, I will just start with just one variable, so it's non-compositional. Let's look at cancer. You have the option between linear and log linear. Usually use log linear. You can group separate by ID. So we want to fit a time series for each of the counties. We have homoscedastic versus heteroscedastic, basically like in the NCI freeware. But what we have that's very interesting, as I mentioned, is for planning purposes, you may want to extrapolate what will happen or forecast. And so here, for example, we are going to simply forecast like 20% of the observed time period. So we are going to forecast over the next 5 years beyond what has been observed. So you can run it, and you see it run very. And so we have a workspace, again, with 4 different visualizations. The first one is actually the time series. And here you see the particular state, and it's being displayed, it's being highlighted here in yellow in the map. So we're looking at the first one by alphabetical orders. And we can move to any other counties, and you can see as we go from one county to the next, it's being highlighted in the maps. And you see also the change here in the time series. Now, you see in this particular case, for this particular county, we have only one joinpoint. And what Vesta does is automatically we select models with, let's say, no joinpoint, one joinpoint, and 2 joinpoints. So we select 3 different models. We try 3 different models. As you can see, as the model becomes more complex, we can go back to maybe that one. You can have a straight line, and then you have, 1 joinpoint, 2 joinpoint. As the model becomes more complex, of course, it's going to fit the data better. But then what's happening is that the number of parameters to estimate increases. And so what you are trying to achieve is use the rules of parsimony and trying to find a balance between a more complex model and a model that fit the data well. And so we're using the statistics called the BIC that measure parsimony. And so the lower the values of these statistics, the better. And so what we can do here is display all the curves, or you can just select and say, I'm going to use only the most parsimonious models. But if you want, you can have access to all the models. In this case, we're going to display in the report only the most parsimonious model. You see in the report, you have all the parameters you use to run the methods, and you have the results for each of the counties. And again, if you want, you can export this report as a PDF file. And what you also have here is you have 2 maps. The first one represents the AAPC. And again, we do that for the most parsimonious models. And so it allows you, for example, to select one county, and I'm going to use select. And it would be one where actually you see that the APC is negative. So that's one of the counties where the percentage of death caused by cancer didn't really increase over time. And here you have some where you see is more red, so which means that the APC is higher. So this is where there's stronger increase in death caused by cancer. You can you can clearly see the difference between this one. So you can look at differences between counties and visualize the time series very easily and the model. And here what you have on the right is actually the value of the model itself. And so if you start using the time slider, that's the one that's going to change on the right. It just show you not the actual observed value, but the model values.
Right.
Now, these are just some of the output. If you look at the data folder, you will see that when we run the method, there is here a folder that's been created that tells you actually also the time when it was run, and it gave you all the output. So we've been looking at the jump run results. We've been looking at the jump run regression, the plots here. But if you want to look at the different values, for example, of the jump run, they can be mapped here. So everything is accessible in the time plot. Okay. Now, the only thing I want to do here is to also apply the method to compositional variables. So in this case, I'm going to say yes, and I'm going to use it to a subset. I want to use it because, I mean, some of the cause of death are pretty rare. So I want to use it to some of the most, heavily populated counties in the state of Michigan. And so what you can do there is actually to select the variables that will be part of the analysis. So here we have the 7 categories of death: digestive, injuries, and others. You need the populations of each county. We can just do it again separate by ID. So we're going to have a model for each of the different counties. It's going to be almost stochastic in this case. And again, I'm going to forecast by 20%. And you see it runs very quickly. Now, what you see is not one curve, but now we have 7 different curves because we have 7 different causes of death, 7 different categories. And you can see the little dots here is because we start extrapolating. So for 20%, so just to try to predict what will happen in the future. Here, what we're going to do, just to have an idea of where we are, I'm going also to visualize, visualize the populations. And I'm going to display it here. So you see these are the counties here. Again, they are the most heavily populated one. I'm going to use a satellite background. And they're being displayed here. So I can again select, let's say, and I'm going to use a select tool. I'm going to select here Wayne County, this is where Detroit is. And you can actually in red, yeah, these are the most heavily populated. Right. So again, when you can select the counties, so you see all the different time series being displayed at the same time. And again, because of the modeling using compositional data analysis, you are sure that for every single year, the sum is going to be 100%. We have the same, we have a jump point regression report that's being created, giving you all the compositional variables that were included in the analysis and all the parameters you used, as well as all the models. In this case, again, we are displaying the most parsimonious. You can look at all, at least in the report. We don't want to display it here because we have 7 curves. We'll have 21 curves. It's way too much. And again, if you want to go more into details, you can always look at the table of the results. I can do just this one. I can put it in workspace 2. So let's scroll it. So these are the results for each of the counties we have. And again, these are only I think 12 counties, and we have all the, you have the name of the counties, and you have all the output variables, everything that is being created. And if you want to export it, you can actually export it as an Excel file and just, conduct further analysis outside Vesta. The same things, if you have a map that you like, you can always export any of the plots, and it's going to be exported as a JPEG file. So, we have option. You can export the report as PDF, every visualization a JPEG, or the data as an Excel files. And I think we are ready for Q&A. I think we are right on time.
Let's see if I can get back to there. So it looks like Q&A. And now to get back over to, I think that's it. Oh, yes, we've already consented. I'm not going to broadcast. Here we are. So I go to Q&A.
Yeah.
All right. So the first question we have has been posed to us, Pierre. Does Vesta calculate and plot confidence bands around the join point regression lines?
Not yet. It's a great suggestion. We have way to propagate uncertainty through the analysis, and actually, this was actually part of the novelty, in particular with compositional data analysis, because we know if we are looking at different variable like percentage of cause of death and so on, based on the population size, and we can calculate standard error. But what happened when we start combining all these variables and create log ratio? And so inside the software, we have this propagation of uncertainty through Monte Carlo simulation, so that we can actually calculate the uncertainty attached to each of the compositional variables, each of the log ratios, and use it when doing the modeling. But we're still working on that part.
So good. Yeah. That should get into our development queue. I think that's an excellent suggestion. Okay, another question. What format do your space-time data need to be in to import to Vesta? Can you show a sample file in Excel to show the format? And can you load shape files and data files separately and merge them? Let me take the last part.
Okay.
There's several here.
Yeah.
So we don't put you always on the spot.
Yeah.
Yes, absolutely. You could load shape files especially to capture your geography. And with them, you can have data associated. So you just suck in a shape file. But then you have other files that are separate, so long as they have a common geographic ID. You can then suck in a whole host of data files and merge them with that particular geography.
Yeah, I mean, in terms of the time format, I mean, in this case, was very easy. It was just simple years. We have additional time format. I mean, it could be day, month. And for the coding, I was actually refer you to the help menu we have.
Yeah.
Because this in the documentation, we show example of this format.
Yeah.
But again, it's pretty easy as long as you have this comment field. In this case, would be FIPS code, so you can merge this temporal data with the shape files.
Right. Yeah. And in terms of showing an Excel file with that particular format, we're not going to do it right now, but we certainly give you those, and some of our examples in the Vesta software provide those. Okay, another question. Why would you only look at the subset of the most heavily populated counties? Don't you lose spatial information in the analysis? Well, that's a good one.
Yeah, I mean, that's the only reason was I wanted to show time series they were more stable, but I mean, there's no reason. It's why actually I wanted to start with only using cancer and look at all the counties, but then I focus on this subset just for the compositional data analysis. But there is no limitations here.
Yeah,
you could certainly do that.
And here we have a compliment and a question from Eric Delmel. Thank you, Eric. He says, fantastic presentation, Pierre and Jeff. Sounds like car talk on NPR.
Oh, good.
But more seriously, do you have competitive pricing for universities and researchers? Yes, we do. You'll need to go to biomedware.com, click on Vesta. I think it's a couple clicks through, and you'll get to all the pricing. It is a subscription model, which means you have to pay annually. But if you're already paying, for example, for Esri products, we're well below those products, and we have no charge ups, right? So there are no, credits you buy. You don't buy credits, you get it all right from the start with Vesta. Right then. I have no other questions coming in. So what I will do is remind everyone as we close that you will receive, probably in a few days, from our wonderful helper here, Juliana, who's put this all together. Thank you, Juliana. She will send you a link to the recording, so you'll have this webinar, and also to all the data that Pierre has presented, the project itself. So what you can do is go to our website, download a 30-day free trial of Vesta, download the project data, and you can then be Pierre Govarts. All right, then. Thank you all. Bye-bye till next time.